This is how you find me on the internet. That's my internet thing handle, Twitter, GitHub, SoundCloud, Snapchat, whatever your flavor is. And the slides and the code for this is right over there on GitHub. I work for SoundCloud. We're based in Berlin. If you don't know, SoundCloud is the biggest music platform on the internet. Right up there with YouTube, I guess, although YouTube doesn't think they're a music platform. These are like some of the artists and content creators from SoundCloud. As I said, we're like quite big. We get like around 12 hours of content uploaded every minute, and we have around 135 million tracks, which is around 4 times more than what you would think a big sound platform is, like Spotify. I didn't say that word. We get around like 200 million monthly active users. So that's a lot of stuff. That's it. As any other platform, I guess we have our own weird challenges. Like like shopping platforms get challenges on the Black Friday. We get challenges when rappers drop their new tracks, and users get very engaged by them, and so we cannot like do maintenance on nodes for a few days because we don't want to lose engagement. We use Scala at SoundCloud. I usually say that SoundCloud is like a company that is a polyglot shop, which is true. But mostly these days we use Scala. We started out as a Ruby shop, so we were like a Ruby monolith, one of the first Ruby monoliths, along with Twitter. And then, basically same as Twitter, we failed to scale the monolith, and then we figured like we're gonna break into microservices or whatever they're called these days. So back in the days, there was like a Cambrian explosion of technologies. The idea was like, if you're up to maintaining the source of whatever service you're building and like being on call for it, which sometimes means like waking up on Sunday at 3 a.m. and like fixing stuff, then like you can write it in whatever. And so everyone wrote it in whatever. But like eventually we kind of converged on JVM, and Scala ended up being like the biggest tool, I guess, in our toolbox, mostly because of like all kinds of toolkit we have around it. Like we have like an internal framework where like spinning up a new microservice is like very easy. You get like a lot of things for free, our telemetry, our like error handling stuff. So like all of that for free. So like if you wanna, that's basically like the tool of choice. But also because historical reasons, we had a lot of naturally good Ruby developers. So they figured out how to use JRuby for their services, so we have some of that. And New York office is very into Clojure. I guess New York is very vibrant, has very vibrant Clojure community, so like they are into that, and they figured out how to twist our Scala framework to use from Clojure. It doesn't look very pretty, but it works for them. But I'm kind of not here to talk about what we do at SoundCloud. I'm here to talk about like a topic that is near and dear to my heart, and that is what you can do, how you can twist Scala compiler in all kinds of weird ways, and use it in a way that the creators maybe didn't like really want you to use it. So, wow, I actually have code here. I guess I'm gonna be like just like showing you some code and then maybe making it run and like we'll figure it out. Yeah. So is everyone actually familiar with like Scala syntax? Who knows Scala? Most. Okay. So this is going to be heavy on syntax because, like, first of all, we're doing things in like in another world, in like compile time world, and like most of the things in Scala weren't like built for that, and so there's no nice syntax for that. And so, like, I really encourage you to look at the ideas and not the syntax, because the syntax is going to be hairy. So this is actually, this is actually syntax-wise, this is fine, right? So what we're doing here is we define a trait that has some operations, and as you can see, like all of those are types. There are like no values around. And then we define two implementations of that trait. This is basically defining a type-level Boolean that has like an AND function, a OR function, and if then else function. And this is the true case, this is the false case. And there's some return case. And so, like, basically the way you would define it is like, in an AND case where it's true, you would return the right-hand side, right? Because like the left-hand side is true, the right-hand side needs to be true for it to be true, or whatever. In the OR case, if it's true, well, it's true. You don't need to look at the right-hand side. In an if then else case, you just return the true case. And the false is basically the inverse of that. If it's false, then the AND is already false. You don't need to look at the right-hand side. And OR is the right-hand side because the left-hand side is already false. And then if then else just returns a false. And then, like, just like using it is kind of the weird part, right? So here in the comments, I basically try to explain in a pseudocode what that does. So like the hash here is a type projection. And so basically, so like all of these are types, there's like not a single value here. So you basically say that this type false has under type projection this type double pole thing applied to this type, and then you want the compiler to prove that like this type projection applied to this type on this type is going to be a true. Let me see if that compiles. Is that large enough? Does everyone see that? I can, yeah, cool. Simple bulls. Let me just copy paste and yeah, so that compiles. Let's try to ask it, maybe it's false, and that doesn't compile, and we get a compiler telling us that it cannot prove that true is equals to false, which what we probably expected, more or less. And syntax for if then else is, yeah, it's kind of weird, but like applied to a true case, we just return the left-hand side, and applied to false case, applied to false case. False. So we would probably expect it to return an int, right? And the compiler to complain, and that's what it does. It says that int is not a string. There we go. And here's like a more hairy example, which is which has like a nested if then else. First applies an if then else to the left part, to true, gets into a nested if then else, and then should return like a right hand side for the false, right? And so like not long, right? So I mean, does this make sense more or less? It's like code, but like at compile time with no, so like there's no values anywhere. Like the compiler proves things about types, and it like gives you a value to hold on to. Like the res6 is a value that proves that a string is equal to string, but like you cannot really do anything with it. Like, oh yeah, you can compose the proving parts together, but yeah, like there's no value level computations happening. All right. So this is more or less okay. Let's move on. What else can we do at compile time other than booleans? Let's try and implement natural numbers. We're gonna implement piano numbers, which is like basically implementing a 0 and a function that takes a piano number and adds a 1 to it. Code. Piano number. Wow, that's very small. Actually, I think I have something in slides. Yeah, there we go. I'm gonna go back to the code and actually show you that this like compiles and runs, because like I don't expect you to believe me that like these weird things are actually valid Scala code. But here's what we do. We basically define a trait for like natural numbers in general. We implement one for 0, which is a z, and we implement another one for a successor function, which takes a natural number and like adds a 1 to it. So this is pretty straightforward. This is basically like applying a function to a natural number. Right? That makes sense. Let's try and, oh yeah, let me actually okay. Piano dot underscore. So, for example, a 2 would be wrong bracket, that, right? And like 1 would be 1 less. Right? Makes sense more or less. So let's try and make this thing subtract 1 from a natural number. So how would we subtract 1 from a natural number? So like, let's make a shortcut, and because we have natural numbers, we don't have negative numbers. So we're gonna, if we want to subtract 1 from 0, let's say it's still 0. There's no you cannot go lower than 0. There's just 0. So there's a lot of things going on here, but basically the main idea of how you do it is you think about the recursive structure, which is how our natural numbers are defined. They're basically a recursive structure with a base case of z, 0, and like an inductive case of +1. And you implement type class instances. Yeah, I forgot to ask about that. Does everyone know what a type class is? Okay, some people know what a type class is. In Haskell they're called type class. In Scala they're called, probably most people call them type class. In Clojure they're called protocols. And they're basically a very extensible way to add functionality to types, including types that you didn't define, that came from some jar from somewhere, and you want to make them do something for you. So let me crash course in type classes. Trade show of type A has a get string of type string. So we have defined a type class called show, and this type class basically, this type class basically witnesses that a type can be converted to a string in a type level, in a type safe manner. So like for types that cannot be confirmed to string, the get string should not compile basically. So this is how we use it. Show for int dot get string. This should not compile because we didn't tell the compiler how to show ints, and it doesn't. So here's how we tell the compiler how to show ints. Show int of type show for int equals new show int. I'm using 2.11. Yeah. Wow. I actually need to define the show, the thing a little bit different because the get string needs to take a value, and then val show int of type show int equals new show of int. I'm writing a lot of types. Probably the compiler can infer most of them, but get string of type int equals I to string. And now when we try to find the type class for int and get a string for 1, it will actually print it. Right, so that's basically the same thing that that Haskell does, same thing that Clojure does. So this is the mechanism that we use to implement a type class, witnessing that you can subtract 1 from a natural number. So the base case is, we just discussed it, 0 minus 1 equals 0. That's what we decided on. And an inductive case, here's what it says. Inductive case says if you have a thing that is a successor, then a minus 1 of that is just like whatever is under the successor. So basically like strip that thing off. That's a minus 1. The aux thing over there, it might be a little bit confusing, but if you look at it, it basically takes the result of the type class minus 1 and puts it into the type parameter over here, so we can make these kinds of claims over here. Because like you cannot like write a type signature that has a thing inside there, right? So after we have that, I'm actually, yeah, I'm gonna Sitly minus 1 of 2. Let's see if that compiles. Yeah, that compiles, but we don't really know what it is, right? Like it doesn't tell us what it is. It just tells us that, like, yeah, I could subtract a minus 1, a 1 from 2. And so this is where we use the aux type to ask it, is it 1? And it's like, yeah, it's 1. And we're like, are you sure it's not 2? And it's like, nah. All right. So let's try to add two natural numbers. How would we add two natural numbers into a natural number? So again, we'll try and recurse on one of them, I guess, right? And here we're going to recurse on the right natural number. And so there's a lot of things going on again, but like if you think about it inductively again, the base case is that when you have 0 on the right, what do you return? You just return the left, right? Easy. That's the base case. It says when I have an a on the left that is a natural number and a z on the right, which is a 0, then I just return whatever is on the left. And what do you do with the inductive case? In the inductive case, you have two numbers. You don't know what on the left is. You don't really care. But you know that on the right, you don't have a 0. So what you need to do is like subtract 1 from the right, like put 1 on the left, and then recursively call plus on those new values. So this is what we basically do here. We subtract 1 from the right. This is the right part. We subtract 1 from the right and capture it into a new value c, which is where we use the aux. And then we recursively call plus on the left side plus 1, right side minus 1, capture it into a value d, and return that. Yeah. Let's see. Plus 1, 2. That should compile, right? But it doesn't tell us what it is. It's just like, yeah, I can add 1 and 2, and we're like, is 1 plus 2 1? Nope. Maybe it's 3. Yeah, it is. Right? So that's slightly harder, but like more or less understandable, right? This is the inductive case. I brought it like, arranged it more neatly so you can see like a return type, some a plus some b equals the d, where d is taken from that. Yeah, read it. Wow. What? There we go. H-lists. H-lists are heterogeneous or heterogeneous lists. Okay, Miles doesn't know, but it's either heterogeneous or heterogeneous lists. Those are basically lists that have values of different types and type information preserved for each value. Believe it or not, they're the same as natural numbers, like exactly the same, except for you actually have like a thing there living on the inside, right? It's the same structure, but like each plus has a thing living, like a value living inside, right? So if you look at it, it's very similar. There's a base case which is a nil, and there's an inductive case which is a cons. You can think about it as like a normal list, except at type level. And the cons basically takes the tail and a value at the head, right? Let me first show you what it is. Import h lists test equals h cons. Let's see, int with h cons string and an h nil. Should be it? 1, 2, 3, yeah. Nope. H nil dot type. because of how I defined the H lists. Because of how I defined HNIL, it's an object, and Scala needs you to like put a dot type there. And so like here's a thing that's at type level is basically a list that has an int and then a string and then a nil. Right? It's not a value. It's type. So how would we construct a value of that type? Well, we could hcons 1 with hcons hello, and an h nil. So that's a value with a scary type, but that type is basically what we just described, right? What? Test. Yeah, so the compiler agrees with us. So, oh yeah, and so that thing basically preserves the types of the things inside, so it's not a list of any. So when you do like dot value, that's an int, or when you do dot tail dot value, that's a string. So what kind of interesting things can we do on a list that I still have like 10 minutes to show you? Let's try and calculate the length of that list. In the same way we basically calculated a sum. So thinking recursively. So the length of the list is going to be a natural number that we just defined. And the base case, so for an HNIL, the length is 0. So we're going to just return 0. This is the base case. Pretty straightforward, right? For an inductive case, what do we know about the inductive case? Inductive case, we say that we know the length of the tail, and we have a head. So the length of the list is the length of a tail, which we already know, plus 1, which is over here. And the length of the tail is basically calculated recursively over here by the compiler. So what happens is when we, for a list like that, like that, when we do implicitly length of test, length of test. What the compiler does is it looks at the whole type. And it's like, okay, I have a head, which is something I don't care about, and a tail. Do I know the length of the tail? Not really. Can I know it? What do I know about it? It has a head and a tail. Do I know the length of the tail? Yes, it's a base case. It's an HNIL. It's a 0. Okay, plus 1, now I know this. Plus 1, now I know that. It should be 2, right? Let's ask it if it's 2. Yeah, it's 2. Sure it's not 3? Yeah, it's 2. Yeah. So now you kind of feel like you kind of can do all kinds of things there, and like it kind of feels like a maybe Turing complete language, like where you can do all kinds of things just at compile time, and then maybe also do some things at runtime if you need to. But it kind of feels like you have to define like the whole standard library. And you don't really feel like defining the whole standard library for all the things. And then this is where Shapeless comes in. It has all these things defined for you, including all the operations. On naturals, HList, it has H-maps, which are defined with type-level literals as keys, which is a different topic completely. So yeah, I definitely urge you, if you're interested in type-level programming, just take a look at that. It uses all the ideas of inductive reasoning about recursive types, basically. And I gave a talk that's called that. There's a prologue in your Scala 2 years ago, where I'm trying to give like an intuition towards how to think about these things, and and then at the end of the talk I would implement a Hanoi tower solver in type level over here. And so basically, all right, so what is Hanoi tower? Like the image in the background is a Hanoi tower. It's like it has 3 poles, and you're supposed to like move disks from the left pole to the right pole, but you're not allowed to put like a bigger disk onto a smaller disk. And so like it's like a toy for kids to like understand how you can, you know, logically reason about things. And so like there are a lot of ways to solve it, and but the way to make Prolog solve it is like very easy. It's a very easy recursive algorithm. You just tell it that you need to move the first n-1 elements from left to right through center, from left through right to center. Then you move that one thing on the right, and then you again recursively move these n-1 things from right through left, from center through left to right. You get the idea, right? So like you take this stack except for that one last thing, put it here, and then put that here, and then put that whole thing here, and like that whole thing is going to happen recursively because we don't have because we basically there's a rule, and the computer abides by the rule. And so like this is very easily implemented in Prolog, and also in type level Scala. Don't really have time to show you, but like, okay, import. All the code is online, so you can take a look. What? Let me try that again. What? Oh, it cannot. Okay. What is it? Piano. There we go. Oh yeah, because I defined the whole thing in shapeless, and I need to import types from shapeless now. Import shapeless. Beam, beam, beam. Are you kidding me? Not, I guess. Finally. Yeah, so as I said, this is again just like telling us that it could solve the problem, but it didn't tell us how to solve the problem. There's like a where do I have it? I have a type somewhere. 2013, change. Just a sec. Yep. So here's a type that is supposed to solve the problem. So if you have 2 things on the left, you move the top thing to the center, then you move the left thing to the right, and then you move the center thing to the right, right? That should be the solution. And let's see if that's the solution. Res move.aux. It is. Yeah, again, I urge you to like take a look at the code, but there's a a macro that Denise Shabalin from EPFL wrote. It's called typelog, where you basically write your Prolog program, and it generates like this kind of structure with implicit classes and all of that. He basically watched the talk that I gave and was like, I can do it with a macro. So that's fun. Do I have more time? I don't have any more time. I was planning to show how we actually use it in production. There's like, you can like, other than fun, you can actually use it in production, and we generate JSON codecs for like serializing, deserializing JSON at SoundCloud using these techniques. I can do a lightning talk later. Thank you very much. This is where you can find all the code and slides, and apply to work with me. Do you have questions? There's a question over there.